think we're on.
Let me check. Yep, we're live.
Hello, everyone. Welcome to today's brand new episode of Corecast. I am your host, Tim.
And I'm Mikey.
This is Sahil. Welcome everybody to a brand new exciting episode of Courtcast. Before we get started, if you haven't already, do join our Discord channel. And if you're watching on YouTube, where we do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern. Do ask us questions during the episode, and we'll get to them. So without further ado, let's get to it. So Tim, Mikey, I guess I hadn't thought about this question much until we were discussing this episode about the simplest theory in physics. I mean, typically when I think of simplest theory, you have all these complicated theories of like general relativity, quantum mechanics, and then you learn like a simpler theory of physics in like high school through classical physics, Newton's laws, all that stuff. So I just wanted to, kind of frame the discussion from that standpoint. So I want us to hone in on like what does a simple theory mean in this context? Like, why can't you just have a theory of nothing as the simplest theory? And then also discussing in the context of like Newton's laws, like why can't you just take that and say, oh, good enough, and we're done. So I guess Tim, I'm going to point any one of these questions to you, however you want to start.
Yeah. I think one of the interesting bits, if for those who are not familiar with physics, like physicists are really obsessed with simplicity, and for good reasons. This is exemplified by one of Einstein's quote. It goes something like this: "Everything should be as simple as possible, but not simpler." And it's a super loaded word. What does that mean? Well, the thing is, in physics, we have a lot of the physical world is very complex, and especially in the era of big science, it's really not easy to pin down on which theory is ultimately correct. So of course, physics is an experimental discipline. We look at data and we see which theory is best supported by data. But beyond that, as we talked about last episode in more details, we don't just use experimental data. We also use some guiding principle to allow us to choose which theory is better, right? Like two theory can explain the same experiments, but that doesn't mean they are all created equal. And that's why physicists use this idea of simplicity, or more, or maybe the phrase Occam razor. Basically, we want a theory that explains as much as possible, given as few assumptions as possible. So this is sort of Einstein's idea that it should be as simple as possible, but not simpler, right? So it sounds not too hard, but actually the devil's in the details. It's actually a very, very difficult task, and what it even means, it's not even like objectively well defined. I'll just leave it at that for a starter.
Yeah, and Mikey, I think it might be helpful. You actually give a very interesting definition alluding to simplicity and via Occam's razor in our previous episode discussion. Maybe you can let the audience know what that was for refreshing their memory.
Yeah, sure. Yeah. Well, first, I just wanted to say that, like, I do think it's funny because people always tell me, like, oh, physics is so complicated. Um, and my initial reaction, I was always like, compared to what? Because I started out as a bio major, right? Like, and I am not good at dealing with complexity, and the number of like words that I had to memorize for biochem just like was way over my complexity barrier. Like, in physics, like, it's way, way simpler than biology or chemistry, in my opinion. So I just wanted to, I don't know, state that opinion. I guess it's an opinion, but just to start. But then, yeah, I think what I was trying to stress upon last week was, really just expounding on what Einstein said and what Tim was trying to say, that a theory should be as simple as possible, but not simpler. Um, in the sense that it should be the most descriptive with the least number of assumptions, as Tim just said. Gosh, I feel like what I said was pretty close to that, but basically, like, it should have the widest range of descriptive power with um, minimal structure. I'm not sure if that's helpful, but we're gonna get into exactly what that means throughout this
That's
episode.
fair. That's fair. That's fair. And then I just want to kind of, I guess take a step back and ask, why are we even interested in going after the simplest theory? Like what is kind of the, other than aesthetic purposes, like how I guess how do you get intuition that that might be the right direction to go down, if there can be such a word as right? I guess Tim, why should we use this as the guiding principle?
I mean, in some sense, there is a bias, right? I mean, because this is the bias of science. Science is trying to explain, and the notion of simplicity is sort of like one step above that. You know, if we're trying to explain, we better have theories that explain as much as possible, and at least from historical perspective, that has been very useful, right? We try to come, there have been many instances where people combine theories to explain the same phenomenon under one theory, and it was successful. Like Newton's laws of gravity, right? It was able to explain, an apple falling on someone's head, and that same mathematical structure is able to explain the Earth moving around the sun, right? Those two are seemingly totally different phenomenon, but hey, like one theory was able to explain both, and people celebrated that, and that's how scientific progresses are made. So part of it is a deeply rooted bias. It's a human bias, and it's also part of the goals of science is to explain more with less, and naturally that lead to sort of this philosophical framework to say, hey, look, because another thing is also practical limitations. Like we don't have infinite data. We can't validate or invalidate all possible theories. So there's got to be some biases, for better or for worse, to tell us which theory is better over another, in addition to just experimental evidence.
Yeah, I think you can almost think about it like if you're choosing between two theories, like which one is a better deal? Have you ever bought something that you thought would make your life easier, but then when you actually buy it, you realize you spend so much time on it that it actually didn't save you any time. It actually was like more work. I feel like a theory is kind of like that, right? Like if you have to put in very little in terms of like work or construction or complexity, but you get out like a ton in terms of predictivity, then that's a good deal, right? If a theory is predictive, but in order to make it predictive, you have to like spend a lot of time and effort and energy wrestling with the theory, then maybe that theory is not as good of a deal. So, I mean, my first answer was going to be like, yeah, it's kind of driven by laziness, right? Like we want the best value for the work. And yeah, certain theories are just better deals. And I think that when we talk about in terms of the economy of the theory, like how much it can explain with as few assumptions or as little structure as possible, that seems to directly correlate with how good of a deal a certain theory is and how much we get out of it historically.
I see, I see. And kind of taking that economic lens, if it's the only game in town, like there's no
Yeah.
other theory, and it's even though you like know this is probably not a good deal, but what other option is there? How do you sort of I guess do you still follow that, or are you just like, no, I don't subscribe to that?
I would say that in such a case, the entire goal of the field is to look for a better deal. And then if no one can find a better deal, like no one can find a better theory, like often what happens is like people try to find alternatives to a theory. And then while working on the alternatives, they kind of find that they're back to this theory that they tried to avoid. It's not always easy to sometimes physics pushes you in a certain way, and that's like a whole separate thing too. Like when different attempts to have like different ideas, if you chase that and you find yourself back in the same spot over and over again, sometimes we take that as a hint that maybe nature is trying to tell us something about the.
Yeah, that's totally fair. I guess like my question was slightly hinting at kind of the whole machine learning AI paradigm. But anyway,
Oh, I thought you were hinting at string theory.
no. I was
Okay.
just anyway. That's a whole discussion we don't need to get into. And then so I wanted to touch upon Newton's laws. You know, in high school when I first learned them, they seem simple and they seem to explain a lot of things. What are the issues with that? Is that there's something better? Or like, can you explain the evolution of how this progressed in some
Yeah,
sense?
I think a lot of people take this idea of simplicity sort of in the wrong way. When Einstein say as simple as possible but not simpler, he doesn't really mean superficial simplicity. Like if
Mhm.
in high school you learn about Newton's theory, force is mass times acceleration. That seems like a super duper simple equations, right? It's able to explain a lot. Um,
Mhm.
but it turns out that it's not able to explain certain phenomena. At least Newton's construct. Like I think Newton's, what is it, his Principia, he alluded to some of that problem that he himself struggled with. So yeah, well, I guess you have to go beyond Newton's force law first. Like first of all, the force law doesn't explain everything. It doesn't tell. Sure, it explains how forces work, but it doesn't tell you where it comes from. So Newton has his theory of gravitation, and it's very simple. It just tells you that two bodies attract each other. But he realized that there was kind of like a critical flaw. He imagined a thought experiment where imagine two planets attract each other, and one of the planet will all of a sudden to disappear. And imagine the planets were many, many millions of kilometers away. He thought about what it would mean in his theory. In his theory, it would mean that the attractive forces are all of a sudden completely gone, completely disappear. And he was very uncomfortable with that because the planets were very, very far away, millions of miles away. How is it that all of a sudden, when one disappears, immediately the other will notice it? There's this spooky action at a distance. And it turns out that he was right. That's why his theory, even though it looks simple, it works in simple situations. It actually does not describe the world, which is actually more complex. And it doesn't satisfy Einstein's criterion. It's as simple as possible, but not simpler. His theory was simply not good enough. I mean, it's simple, but not good enough. And so therefore, and you can try to add some hodgepodge term to make it work, but that will actually make his theory very, very ugly very quickly. And the math will just crumble, basically. And that's why Newton's theory is one example where it looks simple on the surface, but when you dig a little deeper, the core is like ugly. It's like very, very complicated.
Huh. Huh. So I wanted to ask, can we also touch upon another area of complexity, even in Newtonian physics or classical physics, of complexity itself? Like if you have, a bunch of like moving bits that obey very simple laws and give rise to this sort of complicated behavior. Is there anything with that we can touch upon, like
I would,
chaos and whatnot?
yeah, I would say Newton's law is able to accommodate a good bit of that. So you can argue that the theory of complex phenomenon and chaotic phenomenon does follow from Newton's law. But it falls short in many different instances. Like, it doesn't have quantum physics. It doesn't have
Mhm.
relativity. So in some sense, Newton's law is almost like a fairy tale version of the world. It's like Santa Claus, right? Like when you're a kid, maybe the story of Santa Claus, it seems so simple. Oh, there's this Santa will come to you and give you some gifts. It's like a very simple fairy tale, right? But if you dig deeper,
Mhm.
like, well, shoot, like in the real world, who's giving me these presents? You have to go
How did
through
the
all.
kitchen chimney?
Like you have to go through, like, in order to make the fantasy of the Santa Claus work, you have to add all these complex things to it. It's kind of, I don't know if this is a good analogy for Newton's theory. It's like,
I think it is, and yeah, and you know what? It would have worked too if we never discovered atoms. Like, Newton's laws work pretty great for pretty much everything that's bigger than an atom and smaller than a galaxy. So, sure, there's some philosophical questions that it brings up that it can't answer, as Tim alluded to, like these thought experiments. But um, yeah, outside of that, it's almost like we discovered a whole new realm where it doesn't apply, and then that really is what motivated the development of quantum mechanics, I would say.
Mhm. What about thermodynamics, in which you have a bunch of particles moving around? Let's say Newton's laws describe on an individual level, but there's just so much to keep track of that you simplify it further and you go to thermal physics. Is that sort of a like a way of, I guess, would that be a simpler theory, or yeah?
Yeah, I think in the popular, science, some people would argue that the laws of thermodynamics are super simple. It's probably one of the, and also very applicable. Because the ultimate, you can pretty much narrow the theories of the theories of thermodynamics into one word: just entropy goes up, right? But it's very, very unsatisfactory. It doesn't explain, like, I don't even know how to describe them. Like, thermodynamics works very well, but it only works approximately. Like, like entropy actually could go down, but statistically it goes up way more often than it goes down. So it's not an absolute statement. So I think thermodynamics definitely satisfy the simplicity criterion. People have tried to make it more fundamental in that way, but it's falls short because it's just not specific enough. I would say, like, once again, it comes back to the Einstein's quote, right? Like, as simple as possible, but not simpler. Like you can't just say, imagine this: if someone win the Olympics, I don't know, like a track runner is able to run very fast, and you just say, well, why did he win the Olympics? Well, because because entropy increases. Well, that's a terrible answer, right? Of course, entropy increases, and that person won the Olympics. But it's so not specific. You're completely missing the fact that this person is training very hard. I don't know, he gained muscle mass. He generated power. According to Newton's law, his body mechanics was so optimized that he was able to run fast. But if you just say, well, entropy increased, well, you're not wrong. But it's also a terribly, it's a terrible description. It's so non-specific. So I would say, yeah, like thermodynamics is simple, but its predictions are also simple, almost too simple for the complex world.
Yeah, this reminds me of part of a quote where it's like, oh, it's technically correct, but not very helpful, kind of a thing.
Yeah, yeah, I think that's fair. Like, I think within Occam's razor, it also need to be useful, right? I don't know, like in terms of utility.
Yeah,
Yeah.
maybe it's just worth noting the fact that, like, it's not like Newton's laws is a completely separate theory from thermodynamics, right? Like, if you use Newton's laws and you imagine that Newton's laws describe a bunch of particles, then that collection of particles will obey the laws of thermodynamics, and you can derive one from the other. And even more surprising, perhaps, is people have found connections that if you look at Einstein's theory of general relativity, there's a way to actually interpret that um, in the language of thermodynamics. And so one of the things that makes these theories simple is, like, in a sense, you're realizing that Newton's laws and thermodynamics are, in a lot of ways, they are kind of the same theory. They match, they fit together in a certain way, and even general relativity and thermodynamics match in a certain way. So, if these are all really the same theory, maybe every theory is really just one theory. That's a drastic simplification that is kind of like tangent to everything we've been talking about.
I see. So then what are the requirements for a simple theory if neither Newton's laws or thermodynamics, which you just mentioned, are like both, simple in the grand scheme of things? What would it be then?
Yeah, I think one requirement has to be that it has to be simple but specific. You know, like
Mhm.
like physics is a pretty direct discipline. Like you can't just be wishy-washy about something. Like if you have a theory, it better describe exactly like how particles move. Like you gotta dig down. Like you can't just give a wishy-washy answer. Or at least it needs to have something that leads to very specific predictions. I think that's gotta be one of the requirements, yeah.
I'd say so.
Yeah. Okay, so that it needs to be specific. Um, but you're also mentioning harping on completeness as well.
I think okay, well, of course, this is in addition to the fact that it has to be correct, or doesn't contradict experiments. And then
Mhm.
another theoretical requirement is that it cannot contradict itself. I think that's often underlooked. A lot of theories that people randomly cook up actually is self-contradictory. Like it just cannot you don't even have the right framework, you know, like. And I think one
Mhm.
example is maybe not the best example is quantum gravity. A lot of times it just leads to self contradictions. You know,
Mhm.
like is the black hole losing information versus not? I'm sure there are way better examples, but like on top of my head, just couldn't think of it. So just minimally not being self contradictory, and also it needs to have enough interesting bits to it. Like I know in the beginning we say that hey, like a theory about nothing is very simple. Like the universe has nothing, nothing is happening. Like why
Mhm.
don't we like that theory? Well, it's kind of useless. It doesn't. There's nothing interesting going on. You know, like maybe sure the universe. Maybe that is the ultimate truth. Maybe the universe start with nothing, it's gonna end with nothing. But if you don't describe any of the interesting bit in between, like what's the point, right? Like it needs to have some purpose,
Mhm.
I guess. Um, so that's yeah. So like completeness, utility, and just consistency. I don't know, Mikey. Can you think of some of the stuff?
It's hard when we start thinking of like these are the seven things that yeah. So I feel hesitant to like try to outline some like I don't know, like Ten Commandments type thing in terms of like what because it's really like if you asked someone like 10 years ago, they would have said something completely different. Like there's so many ways where in the course of doing research in physics where um people discovered like a version of simplicity that they weren't even expecting, right? Like people might have had a certain idea of what it means for a theory to be simple, and then just completely by accident, it's quite often we find that nature's has an even grander imagination than we could imagine, and that even something that looked really complicated turns out to be really simple. I can say that there are certain tricks that physicists use that have worked over the years as a guiding principle. Like if you want a really simple theory that describes like many complicated things, one strategy is to suppose that there's like a million different complicated types of particles, right? Maybe there's hidden relationships between them. Maybe these two particles are actually can be viewed as like one particle. Like maybe they're just two sides of the same coin. So you can take a complicated thing and hypothesize relationships between them, and that is one way. Taking a complicated situation and understanding it in a simpler way that has worked time and time again. But yeah, that's just one example. There's many others.
Yeah. And so, I mean, it seems to me that like the way physics has progressed, even though it seems like things are getting more and more complicated. You have evolution from Newton's laws to quantum mechanics, and then general relativity, and those two are very complicated theories. But in the grand scheme of things, it seems like those are the simplest explanations for a whole wide range of phenomenon in their respective domains. Is that fair to say?
Yeah, I would go further than that too. Like, because
Mhm.
like even though like yeah, and then in the 1920s, it sure must have seemed like Newton's theory is so simple and quantum mechanics is like so complicated. It's bringing all these new ingredients in. But then after maybe 50 years of understanding it, I think most people would agree now that the theory of quantum mechanics is much, much, much simpler than Newton's laws, actually, if you look at it in the right way. So that's what I meant
Oh,
about, like, and it's totally surprising, like, sometimes when we realize that we have to look at things a certain way for them to be simple. Yeah, but then when we look at it that way, we realize it's actually much simpler than the thing we thought was simple, and that thing is actually really complicated.
I see. I see. So, in some sense, you believe that like physics is actually getting simpler, I guess, but it deals with things that are outside of our intuition, like quantum mechanics and general relativity do not fall under human intuition, or at
Yeah,
least not under my intuition.
I would.
Yeah, I
Yeah,
would say that that's separate from being simple. So that is, I think those two things are often conflated. Like, sure,
mhm.
it's very much true that the concepts in theoretical physics are very far from our like everyday experience, but that doesn't make them complicated. I think people just say complicated as meaning like hard to understand, but they really
Mhm.
mean two different things.
Yeah, I would say that this follows another trend in science. Is that over time we science has become more and more general. What I mean by that is, like back in the days, people might try to explain things like why is the Earth, so and so distance away from the sun, you know, or why are the four seasons hot and cold in that way. Back in the days, people might be very interested in that. In fact, we have entire fields of study like meteorology and all that to study these very specific phenomena. But as time goes on, we realize that these are just brute facts of our universe. It's just that, hey, the Earth happens to be at this XYZ distance from the sun. But in a sense, that fact doesn't really deserve much of an explanation from a fundamental physics point of view. Like, it would be silly for you to build a fundamental physics law to explain this, how far the Earth is from the sun, right? And I think as time goes on, we realize more and more of the facts of our universe might be in that category. And so the goals of physics, instead of the goals of physics has the goalpost has moved a little bit, as opposed to having a theory that explains why our universe is the way it is. Now the theory now has a much more complicated job. It has to explain the why it has to actually explain all the possible universes and how their physics could be. And I think this layer of abstraction has made physics seem a little more complex overall. But really, it's this drive to sort of look beyond our circumstances to try to have theory that explains, I don't know, more possibilities.
Mhm. To make it more concrete, I'm just wondering when you say the word simple, because Mikey, you brought up something interesting, which is that intuitive and simple aren't necessarily the same thing. And I'm wondering if you had a theory, like I'm just trying to think how can we I guess make that more concrete? Is it that theory usually comes with parameters like, speed of light, gravitational constant, or maybe other parameters of interest that get plugged into the theory, and then you get all this phenomenon, or it tries to explain all these different phenomenon. Would a simpler theory just have less number of parameters? So even if the equations that come out of it and the physics that come out of it are not necessarily aligned with our intuition, such as quantum mechanics or general relativity, it would in fact be simpler because it has less number of like things that you need to input into it, like less tweaking, and things come out of it.
Yeah, people definitely, like, you can, like, as I said, for a given concrete theory, you can literally just count the number of parameters, and that is some measure of the moving parts. And yeah, believe me, like, in the old days, I mean, Tim were coming up, like, people wrote papers trying to quantify the simplicity of, like, different types of theories, and try to use that as like a guiding light for which ones to look for, which ones to test for. Um, it got a little bit crazy. I think people took it a little bit too seriously. Actually, yeah, like, I would say it's a good, like, rough guide, but if you just go for the theory that has simpler parameters, or less number of parameters, that there are many times in history when that would have shown to be the wrong way to go. For example, like my favorite example is like, you look at the periodic table and there's like hundreds of different kinds of atoms on there, and it seems complicated, right? But then you realize that all of those atoms are just made of three particles: proton, electron, neutron. Boom, done.
Mm.
But now we know that, protons and neutrons are actually made of smaller objects called quarks. There's actually six quarks, and there's all these particles in the Standard Model. So we went from like protons, neutrons, just three particles, and now like when we look deeper, we actually see something that seems more complicated. But it only looks more complicated. We know that the theory of quarks in a lot of ways is much simpler than the theory of protons, electrons, and neutrons, because it doesn't just describe what we see, but it describes relationships. We see why the neutron and the proton have such a similar mass to each other. They're almost like twins if you ignore their charge. Understanding quarks helps us understand why that is, because they're both made up of objects that are really just one object, and they just twist in a certain way, and then one gets a positive charge, it twists in the other way, and it gets a neutral charge. So that's one example of like, when you look deeper, the number of parameters increases. So just naively, you would think that the theory got more complicated, but then once you spend time understanding it, you see that it's actually a lot simpler in a sense, but not simple in the way that you thought. Like if I thought that having less parameters just means simpler, then I would have missed the point. It's great other kinds of simplicity that I didn't even think of.
Yeah, I know it seems like we're kind of dodging the question, and partially we are, because it's very much it's very much an art. It's almost like judging an art piece. Like, how do you judge it? You can try to count the number of strokes that goes into the painting and judge, hey, is this painting good or bad? I mean, on some level, they'll give you an answer, but it's just not this is sort of like counting parameters, right? Like it'll give you some indication, but not necessarily. Like sometimes you really just have to look at the architecture of a theory and just make a subjective statement. I think that's why people write papers defending, why they study certain theories and say that, hey, look, my theory is actually better than X, Y, and Z, and this is what makes a physicist, I think. Yeah, the theoretical physicist, anyway.
I wonder, is there any connection with, say, computer science? Because computer science has a definition of complexity. There's a definition of efficiency and whatnot. Is there anything like that in physical theories?
I actually think it's almost like the opposite of computer science in a sense, where like computer science, like, right, there's like a huge complicated taxonomy of different different what modes of computing or methods for computing, different categories of them, and I feel like it's more like, and none of it is like, it's all human invented. So like, whereas in physics you can't just invent random things. Like it's not going to work. Like you're going to run into problems. Well, I guess in computer science you can run into problems too, but and that's why computer science is so ugly, and that's why physics is so beautiful.
Yeah,
facts here.
I guess that's the fundamental thing, right? We truly believe that what decides what physical law is correct or not is completely out of our hands. We are really trying to describe nature, and we are not we're part of nature, but we don't dictate the natural laws. So in that sense, like, it's not up to us. Like, who gets to be the judge of simplicity? Ultimately, is nature. Like, we can argue all day long, but we're trying to guess nature's game, and that's different from it, and that's why maybe we'll never be able to pin down what it means for law to be simple. That will always be this level of artistry.
And I'd also say, like, there's also like a lot of it is also like hope, right? Because if the truth is not sufficiently simple, then maybe humans just have no chance of understanding it. Maybe it really is like trying to teach a monkey calculus. Like, The human brain is limited in the amount of complexity that well, I don't know, maybe not. But one thing that's for sure is we make tremendous progress every time we can find a way to simplify our conceptualization of something. Once some description gets too complicated, you see progress just slow down there. People just can't wrap their heads around it. And then sometimes it just takes like a new conceptual advance that makes everything simpler. And now everyone can work on it again. And now we see progress. So there is that aspect of it too.
So I would say in the spirit of parameter counting, there is a better metric, there's a better counting exercise that physicists can do to quantify simplicity, and that is similar to what Mike was saying. You can also almost count it as the number of relationship, or more broadly, the amount of symmetry a theory has. So physicists generally believe that the more relationship a theory has, the more beautiful it is, and the simpler it can be, because there's so many different relationships. So even though the number of parameters might explode, but they're all related in some ways. They're all these hidden relationships. So if you like that angle, people have argued that the simplest theory should then be the most symmetrical theory, if you follow that train of thought.
What is the most symmetrical theory? Maybe that might be too abstract of a question, but how can a lay person understand what is the most symmetrical theory?
The most symmetrical theory is one where everything is the same as everything else, because that's really what symmetry means. So when we say when we say symmetry loosely, I think I'll stand by what I said before, is we really just mean that these two things we thought were completely separate, there's actually a relationship between them. They're related in some way. As Tim mentioned, like there's two parameters you think they're different, but you might realize that these parameters are actually part of like a two-component object. And that object, if you write things in terms of that, then it's really simple. Wait, what was like? Oh yeah. So it's like I would just like for just in a real layman's way, like you can think about it as like if I look at a cube, right? I can think about that as a theory of like 8 points and however many edges, or I can think about it as a theory of a cube. And if I notice that all of these 8 points have a very specific relationship with each other, namely that they lie on the vertices of a cube, then now I could describe that entity as like with one very simple, well-defined description. And a cube is just simpler than 8 points. That's what we mean by describing something with a symmetry.
Yeah, and let me just...
That makes...
Yeah, and yeah, it's interesting you mentioned what is the most symmetrical theory, and this is what inspired today's episode. Actually, there's a paper published by Akani Hamed, I think 2 decades now, 2000 something. The title is just called The Simplest Theory, and there he argued for what probably not what most of us would say the simplest theory, but he argues for that. The simplest theory is ones with the most symmetry, what Mike is saying. There are the most number of relationships between particles, so they add supersymmetry in it, where fermions and bosons are the same. We have previous episode explaining what fermions and bosons are, and not just that, he has the maximum number of supersymmetry, where every particle is related. And it turns out that when you do that, and you also add infinitely many particles to it, this is called the n equals the large n limit. They say, just imagine the strong force. The strong forces that we have has 3 colors, but just imagine infinite number of colors. So you have infinitely many particles. Looks very complicated. They are particles of forces, particles of matter, fermions and bosons, right? But then they're all related to each other. When that happens, you actually have you actually get more symmetry than you bargained for. And this is the largest infinite symmetry group, I think, known to physics so far. I think that is correct. it's called a Yangian symmetry, which is like an infinite. But people have studied the consequences of this theory for the longest time. It's also related to amplitude-hedron. I won't go into details, but in that paper, yeah, this is what happens when you take this idea to the extreme. What is the theory with the biggest, maximalist, largest symmetry? And people have come up with that theory, and it is the n equals 4 supersymmetric theory with infinite number of particles. It's the basis for the amplitude-hedron, and so that's the answer for that question.
So are you saying that the number 4 is really large, or you said like n, large n, and so you're saying n equals 4?
Sorry, they're different n's, right? So n equals 4 is the maximum amount of supersymmetry you can get. There's another different n. It's how large how many numbers of color, which is totally separate number, and you jack that up to like infinity. As large as possible. The larger, the better. And technically, supersymmetry can go to 8, but that would have to involve gravity. And I think you can argue that that's even more more symmetry. But it's in the same vein, right? So yeah. So people have tried to take that logical extreme. If you equate simplicity as symmetry, just drag it all the way up. This is the most symmetric particle physics theory.
I wanted to touch upon that. That's actually a really interesting point. Is another way, I mean, you mentioned color, but is another way to relate it back to, say, electromagnetism is you can think of it as a different kind of charge. Instead of like plus minus, there are these 3 different like charges in quotes.
Yeah, Tim saying the infinite charge theory, where there's an infinite number of charges.
Yes.
and so I wanted to ask this question that in electromagnetism, you have attraction, repulsion, and like charges repel each other and opposite charges attract. Similarly, in the strong force inside the protons and neutrons, you have quarks that are different colors, and different colors would attract each other, and same colors would repel each other. And then if you were to take that to infinity, it would basically mean that your chances of coming into contact with the same charge would basically be 0 because there'd be an infinite number to choose from. And that resembles gravity. So is gravity actually the simplest theory in this case?
Yeah, actually,
credit to you, Tim, for mentioning this many times in previous discussions with internally.
That is actually true. That's one of the great discoveries, and that's one of the reasons why people like many different colors. Not the real color, but like take the number of charges to infinite. And it's true that when you do that, your theory looks like gravity. And it turns out that there's this law in physics where if you just double this theory, very naively, because you have n equals 4 supersymmetry, you double that, n equals 8, all of a sudden, gravity comes for free. And people believe that it's not an accident. It might have to do with string theory, but it just comes for free. And these like certainly this doesn't describe the real world. In the real world, we don't have a bazillion different charges, different colors. But just maybe some of that, somewhat like you can't help but feel like some discovery has been made. Somehow gravity can force out of theory that doesn't have gravity to begin with. So you could argue that, hey, this sometimes we can make discoveries even without experimental evidence, just through pure pursuit of this simplicity idea. So that's one instance. And indeed, a large N theory is gravity and has to do with duality, string theory. It's a whole host of involved theoretical ideas, but not going to get into details at this point. Very complicated.
Yeah, that's fair. Mikey, I'm gonna put this question on you since you look really ready and excited. Where the bajillion particles at? Where are all these particles? Like, where's all the symmetry? Why? I mean, clearly don't see this. What's going on?
Well, I would say that the theorist Tim talking about, like, you could think about it more as like an example of how a theory could have almost like just a few parameters, like two or three, and then describe an infinite variety of stuff. Like it's like it's an example of that that we can use to get almost to get ideas even for how it could apply to our universe. Even though, as Tim mentioned, yeah, we all know that it doesn't apply to our universe in that exact form, but literally not just an infinite number of but an infinite number of every single type of particle, all with
Mhm.
this crazy intricate web of relationships that looks like a crazy snowflake pattern. Yeah, I would say it's a shining example of how a theory can be incredibly, infinitely descriptive with almost no parameters.
Yeah,
Hmm.
I would say it's a little bit counterintuitive, right? Like I know online there's a lot of discussions say, oh, string theory is useless. It predict all these things that doesn't exist for our world. But physicists aren't crazy. There's a reason why people study these things. It's because they follow this simplicity frontier, even though on surface it does not look simple. But I'm gonna play a little bit of devil's advocate here because, like, sure, we know that our world is not that symmetric, but because in quantum physics we study possibilities. Like our universe is just one out of potentially infinitely many possibilities. It's plausible that maybe our universe is not symmetrical, but if you look over all possible universes, maybe our neighboring
Hmm.
universe will be a little different. Maybe instead of 3 color they have 4 color. I mean, if you sum up all the possibilities, maybe you will have all the infinite variety of the different colors. And so maybe in some sense, this very symmetrical this crazy theory that has every possible thing together, it might be the starting point of not explaining our universe, but explaining all possible universes. That's why it looks so crazy. It's got all this possibility. So that's one viewpoint where it's not useless to study theories that are totally not related to our world, but maybe it relates to all the possible worlds in this way. Um, so that's one thing one might want to keep in mind.
Yeah, it actually brings me to something I wanted to ask about, which is exactly what you mentioned. That say you have a theory, the simplest theory that just describes all the universes, but then you can't really know like why did we end up in the universe that we ended up in. It seems sort of like a cop out that I'm going to explain like everything, even the stuff that you can't like observe, and it just sort of it just happens that we're like in this. It kind of seems like why can't the simplest theory just be like there's some random process that happens, random, maybe not in the classical sense, more in the quantum mechanical sense, but for some definition of random, there's some random process, and we're just happen to have this conversation, and physics happen to be the way it is, and that doesn't seem very satisfactory. So this way of, as you're explaining it, like explaining all possibilities, but not being able to explain like why we're in the possibility that we're in, it seems unsatisfactory. I'm curious to gauge your thoughts about that.
I would agree with that. I mean, in a sense, you could say that the simplest explanation for all of this is that we're Boltzmann brains, right? That is super simple, right? Like I'm just saying that there was a random fluctuation and that explains everything, right? But um, that theory is not a good deal in the way that's like it hasn't driven any technology, it hasn't, and there's reasons why, yeah, because it's not. Yeah, sure, it could be potentially infinitely descriptive. Literally, it is. It describes everything you can possibly imagine, but um, it only describes as much as you like. It doesn't like. Okay, then I'm a Boltzmann brain, and you're a Boltzmann brain. Everything's a Boltzmann brain. Like, I have to like apply this at like versus like just having one idea that just gives you more and more predictions that you didn't even know. So, yeah.
Yeah, I guess from from this economic frontier, yeah. I mean, in some sense, maybe we have come full circle, right? Like, we try to push simplicity, and simplicity got more and more abstract, and now we're talking about, in order to push simplicity, we push a theory about all possible universe, and I think some very prominent physicists have raised a concern, and this is where some of the hate for string theory is coming from. It's like, hey, look, you're describing all these possible universes, but you're not describing the one that we have. There's certainly some legitimacy into that, but at the end, it is the artistry, right? Like, where do you draw the balance? And it could certainly be true that some facts, brute facts about our universe, it's not worth explaining. Like how much dark matter we have. Maybe it's something. Maybe it has something to do with fundamental laws, or maybe not. Like how many forces that we have, 3, 4. Maybe it has nothing to do with anything, or maybe it is super important.
Yeah,
Unfortunately,
and maybe we can find a way to connect that to the idea that there's some big description across multiple universes, and we're looking at one piece of it. Maybe we can find a way to connect it to that idea.
Mhm.
Maybe not. So these are all we have no idea. Um, and I would say that, like, yeah, just to, about that whole string theory thing, right? Like, I think that's definitely like a historical cultural component, because there are so many instances in the history of physics where things seem to be getting simpler, but in order to get to the next stage of simplicity, things have to get complicated for like a bit. Um, Sometimes to get to that next level of simplicity, you have to take a path towards something really complicated, and then you realize, oh, it's actually on the other side, it's actually way more simple. And so there's so many examples of that in history. Like, I think a lot of people, even though you could argue we might be in that picture with string theory right now, like there's a large group of people who are like, no, no, let's just see where this goes, okay? Like, I know things are looking more complicated now, but we've seen this before. Let's not get our, everything in a bunch. Let's just like give it some time, you know?
yeah. I
I
mean, I think if you like this capitalistic, lens to physics, then it is very much like the stock market. I mean, there is a true value of simplicity somewhere, but it's going up and down. We don't know. You just gotta, probably history tell us that the best approach is somewhere in between. Of course, you probably shouldn't push the simplicity or symmetry down all the way up to 100%. You can end up with these crazily symmetric theory. But also, I don't think you should totally dismiss it either. You shouldn't dial all the way to zero and be like, oh, this is worthless. String theory is worthless, right? All this supersymmetry stuff is worthless. You shouldn't do that. Somewhere in between, so that, I don't know, if you like the stock analogy, it's like you gotta take, a reasonable risk, so that hopefully at the end we'll get to the most utility theory, I guess, the most bang for our buck, right? So
Mhm. Yeah. One other question I wanted to ask is, in this desire to go to more like simplicity and for how we've described simplicity, uh, as you're going down that path, what if what you introduce is simple, but it just, explains a bunch of things, but also creates like a whole bunch of other problems that, you didn't foresee. So for example, in the case of like, actually, I wanted to tie this to experimental evidence. So take the theory of inflation, for example, where they say in the very early universe there was this extremely rapid expansion, solves a whole bunch of problems, flatness problem, all sorts of things. And we've talked about this in a number of previous episodes. And so, but yet there's no like you weren't there during that period of like rapid inflation. So I'm wondering, experimentally, if you're not able to verify it, but you come up with this explanation that solves a bunch of problems, but still has the elephant in the room, like, oh, like what about the actual phenomenon itself that gave rise to all these things? Similarly, in quantum mechanics, you have this concept of a wave function, but you can't directly observe the wave function. You like throw light at something, you observe a particle in a particular state, and that's it. So I'm wondering, like, with those two different parts, how do you sort of think about this?
I would
Yes.
say that like when I think about inflation, like is the theory of inflation, is that a good deal? Is that like economically a good deal? And I think your question highlights how much that it depends on what your values are, right? Like what do you value?
Mhm.
That'll determine whether it's a good deal. Yeah. So questions like inflation, if you value like only value experimental evidence and repeatable experiments, then yeah, the
Mhm.
theory of inflation is not going to be a good deal for you. But if you
Mhm.
value uniqueness and consistency, and like you mentioned, like being able to solve all these problems and uh, with a common explanation and unifying concepts, like theoretical concepts, if you value that, then it's a great theory. And that's totally, reasonable people could disagree about that all day long, for sure.
Mhm.
I mean, like what Mikey said. At the end of the day, yeah, all of our theories are not as simple as possible. Because we don't know. All the theories have some problems with them. Life is not simple, you know. Um, and part of that is comes down to personal style. But I would say for quantum physics, most people will be okay with wave function because it comes with other benefits. And it's plausible that there may be a better formulation of quantum physics that doesn't have these baggage, yeah, and maybe it will
Mhm.
lead to new predictions. And if someone is able to come up with it, great. Maybe they would even win a Nobel Prize. But then I think right now the field does couldn't find a better deal right now. Like there's no
Mhm.
better there's not a better theory with better trade off. But of course that trade off is also subjective. You know, you get to decide. You know, there's some people who really don't like quantum mechanics. They're still stuck in this classical world. They still couldn't give that up. And
Yeah, we know a lot of them.
yeah, and you know they're free to be stuck in that land, but for many of us, I think that trade off is worth the jump. At least I would say quantum physics is like 95% there. Maybe 5% it's a little not correct, but like hey,
Mhm.
it's close enough. Maybe there will be better replacement, but probably not that different.
Tim, just for my own curiosity, are these people, do they subscribe to pilot wave theory? Is that what you're referring to?
Something like that. Something like
Okay.
that. But then I don't think they
Okay.
can be particle physicists because
They're
it
all
just doesn't.
old. They're all really old.
Yeah, and I would say so a lot of times when I look at like people who stuck in a different value system, kind of like hey they value different things more. I would say sure even if the prevailing theory is wrong, there is no way the correct answer is for you to hold on to some old notion. You probably need to be crazier. It needs to be more drastically different. So probably yeah, even if quantum physics is wrong, I'm not gonna
Mhm.
hang on to old classical physics idea. I'm gonna embrace something even newer. So that'll be my personal bias, right? But every generations have their darling theory, basically. That they you know even
Mhm.
Einstein says God does not play dice, but you know
Mhm. Yeah, that makes sense. And so we're almost at time, and so wanted to, in our tradition, give you a chance to leave the audience with any words of wisdom that the simplest theory or most symmetrical theory of physics has taught you.
Yeah, I think just super quickly, I think, like as we mentioned many times, and kind of emphasize here, our goal as physicists is to look for the simplest possible theory. And I think the most important thing to keep in mind when you're looking for the simplest possible theory is do not overly rely on past notions of simplicity. If
Mm,
you restrict yourself to applying your previous notion of simplicity to find the next level of simplicity, that's like I think history has just shown that that will never ever work. It's always going to have to be something radically new that no one could have even dreamed of.
mm.
Yeah, I would say that this title, maybe the answer is cliche. The simplest theory, no one knows. In some sense, you have to look into the mirror and judge for yourself. But but if you buy this idea that simplicity is symmetry, we do have an answer for you. Then I will refer you to the paper called the simplest theory, where we jack the symmetry dial to the max. As many symmetry as possible. Then for now, that will be the simplest theory possible. But is it the simplest theory forever? Probably not. So we're still searching, I would say.
Yeah. It seems like, Tim, we've kind of come back full circle where you mentioned that the theory has to be useful in order to be simple. And now we're talking about a theory that's the most symmetry, but it's unclear if it's useful or not.
We have come full circle. It's exactly true. It's showing you that anytime you take a principle and dial it to the extreme, you end up with some Frankenstein thing. But you do learn something along the way. Like, I don't know if that's a good lesson or not.
That's fair. That's fair. All right. So on that note, I want to thank everybody for joining us, and we'll see you all next week.
Yeah. See you all next week.
Bye.
Bye bye.